sign that maybe.
Well, good
if
evening,
there's
everyone.
business a
Welcome
little-
to the May Smpte New England meeting. A few announcements. We have some things coming up, some exciting things. Tonight, we're thrilled to have with us not only the Senior Video Application Engineer of Tektronix, but also the Chairman of the Washington, D.C. chapter, Karl Kuhn, to speak on video and audio quality throughout the broadcast chain. Welcome, Karl.
Thank you. Welcome, everyone. I appreciate you taking time out of your incredibly busy schedules to come here tonight. I'll try to make it well worth your while, so you walk out of here with some practical knowledge. And I enjoy speaking up here in Boston because it's a very healthy section from what I've seen in my visits up here over the last few years. And I take Smpte very seriously. I'm involved as a section chair in Washington, D.C. And like many things in life, the more you invest, the more you give of yourself, the more you get back. It pays dividends. And my experience with Smpte has definitely proven that for me. So if you're not involved, I encourage you to get more involved. So with that said, try not to run over too late tonight. I realize it's nice weather and there's a hockey game on TV and all that stuff. If you need to leave early, feel free.
No, we all want to be here.
I know, or else you wouldn't be here. So as I said before, I appreciate you guys being here. Tektronix, application engineer, cover the Mid-Atlantic, Northeast, Eastern quarter of Canada. Like to spend a lot of time up here. I have friends and family in the area, so it's always a good excuse to come up here. As far as maintaining video and audio quality, this is kind of a high-level overview. Yes, a lot of experience in the room, from what I understand, so I won't go in too much of the basics, but try to give you some fundamentals, some real practical knowledge from my years of experience in the digital world, as far as things that might help you. So that way you have trouble or problems at work, you might say, gee, I'm glad I went last night because I learned what I can do or how to get closer to solving the problem that we have, or just reinforce the knowledge that you have so you have more self-confidence when a new issue comes up. When you're in a group environment and you're not quite sure, but this maybe give you a little more confidence to speak up and say, this is what we need to do to fix this problem. Because in the digital world, at one time, don't worry, it's digital. Don't know if you ever heard that in your career, but been with Tektronix 11 years, 20 years before that as a development engineer with IBM. My first digital project was 1994, and pretty much that's what management told me. They brought me into the group because I was responsible for audio and video quality on various IBM networks over the years. And this is the first digital network. Got involved with the Hong Kong Telecom and Bell Atlantic VOD trials and whatnot. It's digital. It just works. Well, wouldn't that be nice if it did? Because if it did, we probably wouldn't have a job right now. So it doesn't just work. Keep in mind, analog degrades gracefully. I like to use the medical analogy. It's common ground, most people understand, that analog tells you all its aches and pains. It's a very cooperative patient. With the years of experience that you have, your trained eyes, your trained ears, the patient is communicating with you. You can look at the picture, listen to the sound, and it's telling you all its problems. You can see countless problems. You can see high-frequency roll-off, chroma-luma delay issues, noise, beat frequencies, multipath issues, on and on and on, just by looking at it. Because what you're doing, it's a window into the electronic world. With your eyes, you're connecting with the electronic world. It's the same thing with the audio. You can hear distortions, equalization issues, crosstalk, hum, hiss, on, just by listening to it. So with your years of experience, the patient says, I have these aches and pains, what do we need to do about it? But typically, the way to look at it in the analog world, it's up to you, is it good enough? I'm sure at one point in your life you have a little portable TV with rabbit ears, you're gonna watch the big game, your favorite show, you fiddle with the rabbit ears, an airplane flies over, you have multipath flutter, the signal's in and out, chroma comes and goes, but you've decided that's good enough. I'm going to watch the game or my favorite show. Digital has a cliff effect. It tells you basically nothing. Medical analogy, the video patient walks in, I feel great. Well, they look good, they sound good, and they fall over dead. Gee, I wonder what happened. They seem perfectly healthy not that many seconds ago, because digital decides when it's not good enough. Not
We always
using.
like to say that the digital picture always looks perfect.
I got to remember that one. That's a good one. Digital decides. It looks good, it sounds good, well, where'd it go? You might see some blockiness, some artifacts, some pops, clicks, some stutters in the audio, whatever, but it just basically goes away because digital decides when it's not good enough. So what you need to do in the medical world, it's nice to have a baseline of the patient. You go to the doctor, you have a history, the patient's been great for a while, okay, then they come in, things aren't so good. It's nice to have a baseline. Months, years of history to say this is what they were like when they were healthy. Now they're not so healthy. What is the same and what is different? Medical analogy. You look at the results that came back compared to results over the last few years. If it's the same, that's probably not the problem. If it has changed, that's where you want to do more testing. Focus on it. The sugar level, the kidney function, whatever it is, well, with video, it's the same thing. Digital domain, if it changed, that's what you need to pay attention to. So baselining your system, that's great, but this uncooperative patient, you want to run your facility like an intensive care ward because the patient's not very cooperative. I don't know if they're healthy or not healthy or what's happening behind the scenes. So in intensive care ward, you have all these probes, all these analyzers, all this measurement equipment out there looking at the patients to see if something changes. If something changes for the worse, you have an alarm, you react, you try to avoid problems, try to keep the patient alive. That's what we do in the land of video. So you need probes out there looking throughout your entire network 24/7 to see what's happening. Interoperability. That's really what we're trying to achieve. In digital, interoperability is the rules of the road, like the rules of life. If you follow the straight and narrow, you'll probably be okay. If you say, well, rules don't apply to me, that's something else. You decide to get in your car, be real careful, get on 128, follow all the rules, you'll probably make it between point A and point B. You get in your car and say, the rules don't apply to me, watch out world, here I come. You might not have a very smooth trip. It's the same thing with a digital signal. Interoperability of the rules of the road, the standards, the recommended procedures, the engineering agreements that we have. A signal being created in one device needs to follow the rules of the road so the receiver can follow whatever's being sent to make some sense out of it. If you bend the rules, a certain receiver might say, okay, I can deal with that. Or if you have a big network with many receivers, certain receivers say, I'm okay with that. Other receivers say, no way, forget about it. I'm taking the rest of the day off. I don't understand your signal. And another receiver might be intermittent. Well, maybe I will, maybe I won't lock, I'll unlock, whatever. So interoperability is very important. A big circuit board. Remember way back to the good old days, you pull out a circuit board, you can see the resistors, the transistors, a transformer, a capacitor. You can just look at it and say, here's the power supply, here's the front end of the RF, here's the final output, here's the AC, the DC, the high voltage, the low voltage, just by looking at it. Look at a schematic and say, where are my test points? What probe do I need to see the signal at that test point? Where is the problem? Where isn't the problem? You go through the flow of the circuit. It's good, it's good, it's good, it's bad, it's bad, it's bad. Well, right here is where it went from good to bad. I need to focus and figure out if the problem is there. It's the same way in a small video network, the same thing in a global video network. Where is the problem? Where isn't the problem? What are my test points? What do I expect to see? What probe do I use to connect to that point in the network and see what's going on? Something I learned the hard way in the lab back at IBM, testing is too expensive. It's digital, it just works, we don't need test equipment anymore, this is a new world we live in, and equipment is just too expensive. We don't need it. So here I was responsible for audio and video quality on global networks with no test equipment. So basically a mechanic without a toolbox. Well, I hope it works. If it doesn't, if we can't reboot it and reset it, we're out of luck. Management, I would walk in, say, I need this for this project, for Hong Kong, wherever it was, and they would say, no, you don't need it. End of story. I go back to my queue and I sulk for a few days and say, do I have a job? This is no fun. I need some toys. I have a lab to run. Wasn't any fun. So what I learned, I spoke to the IBM attorneys, that helped. What is the cost of not testing? Can you afford that cost? If the signal goes away now and never comes back, does anybody care? I would hope so. There's no reason to be doing what you're doing. IBM, they said, we have contracts, we have a reputation, we have to have quality. Well, what's the risk? In your business, what is the risk? If the signal goes away and never comes back, is it revenue, is it reputation, is it life and death? What is it? What is the value of things working correctly? Well, there's a cost to maintain that. So once I figured out how to talk to management in dollars and cents, I need this to maintain this quality to keep these problems from happening. Can you cut that list in half? Sure, I can do that. I can cut the list in half. And you always have a wish list for when it comes along, a new project. Here is what I need to get my job done. Well, we'll get half of it this time. I can do that. So you have to have a business case for why you're doing all this. Breaking the law. There's enough ways in life we can break the law, enough ways in video and television we can break the law. Going outside your spectrum, the wrong content, wrong time of the day, the wrong advertising, on and on. Now we have audio loudness. I won't spend much time on this, but it's kind of a block diagram. I think we have enough experience in the room, but I'll fly through it real quick. We have a camera taking light energy in, converting it to an electrical signal, RGB, red, green, and blue. That's how you get all the colors of the rainbow, all your shades of gray. Or it could be a computer graphics system working in RGB. We need to get out of a parallel technology. This is 3 or more wires between point A and point B. First thing we do is we go from RGB to color difference, where we give one channel to shades of gray, and we add, subtract color through the 3 channels to get all our shades of gray and color. Back in the old days, we had composite, we had digital composite, which is long since gone away. What we're going to focus on is component digital video. So we make an A to D conversion. We do sampling, how many samples, you use Nyquist, what's the frequency you want to maintain fidelity at, and then go at least twice that. How many ones and zeros? We want it to look like a fax machine, ink on, ink off, but to look like television, shades of gray, different colors, so you need 10 bits or more typically for your color information. Here we have 3 wires between point A and point B. Here we have 3 wires. We do a 10-bit sampling between my luminance and my color, so we go from 3 lanes to 30-lane highway. It's the wrong direction to be going, because the problem is with parallel technologies between my laptop and that projector, it's a very short horse race. The signal leaves here and it gets to the finish line, all the ones and zeros pretty much the way they left. The longer the run, the more parallel technology starts to fall apart. The longer the horse race, everybody doesn't get to the finish line at the same point and the signal starts falling apart. So you want to get a parallel as soon as you can. Here from 3 to 30 wires, it's the wrong way to go. We've increased the frequency from analog digital conversion. It gets messy. What we want to do is serialize this, serial digital video. So we do some time multiplexing. We take a luminance sample, 10 bits, put that into a 10-lane highway. We do a 10-bit sample of R minus Y, 10-bit sample of Y, 10-bit sample of B minus Y, and back to Y. So we're half sampling the color difference. We're always sampling luminance. So we went from a 30-lane highway to a 10-lane highway. Then we do a times 10 function. For example, out here on 128, I-90, whichever, the turnpike, we were lucky enough to have 10 lanes in one direction, everybody loafing along at 60 miles an hour. Life is good. Blinking sign says 1 lane ahead, construction. It's disaster. It's the end of the world. It's traffic jams. In the world of electronics, we can do a times 10 function. 10 lanes parallel to 1 lane 10 times faster. We do serialized digital video. So 60 miles an hour, 10 lanes wide, blinking sign says 1 lane. Everybody goes through the construction zone at 600 miles an hour. There's no traffic jam. The troopers wouldn't like that out here, but in the world of electronics, we can do that. So we do a serialization. We're up to 270 megabits per second for SD, 1.485 for HD, 3 gig for 1080p and above. It gets messy storing that. It becomes impossible to transport it. You can't fit that much information into a 6 megahertz channel. 1.5 gig would consume an entire cable network with 1 channel of HD. Not much of a business case doing that. So you need compression. MPEG-2, H.264, whatever, we squeeze it down based on human vision model. What you see, you keep. If you don't see it, don't miss it, you don't send it. That's how we get the lower bit rates from 1.5 gig down to 15 megabits, for example. Then we transport that, transport stream, and then we do a decode, and if everything worked, you have quality audio and video. This is an eye pattern. 2 big eyes looking at you. I'm still amazed. I go to facilities and they have no test equipment that can see an eye pattern. So essentially they have no test equipment that can see what's actually going through the cable, the infrastructure they have in their entire facility. Well, the waveform looks good. Well, the waveform is derived from 1s and 0s going through the coax and all your circuitry. So you need to be looking at the eye pattern. Like the eyes in this studio here, the more open this is, the more information is being transmitted correctly. Everybody's eyes start to close in the audience. You hear what Karl says, and you're thinking about the weekend and the nice weather and the hockey game, and Karl's a distant memory. The information is not being transmitted as intended. It's the same thing in the physical layer. This is 800 millivolts, less than 1 volt. Now much of a signal going through our facilities, 800 millivolts. This is time, this is voltage, like an oscilloscope. What you're doing is you're overlaying thousands of transitions of 1s and 0s going through your facility. So picture these 1s and 0s zipping through a piece of cable. The laws of physics unfortunately apply to television. Rise and fall. Let's say 1.5 gig. To get a rise and fall this steep of a bit rate of 1.5 gig, you need to go out to the 3rd order harmonic. So high frequency. This is the challenge. Cabling is a nice low pass filter. It does not like to pass high frequencies because the laws of physics apply to TV. You go outside tonight, you see a beautiful red sunset. You don't see a blue sunset because the high frequency gets attenuated by the world that we live in. Any Navy people in the room? Sonar. When you're going under the polar ice cap trying to avoid hitting the bottom of an iceberg, you're putting out high frequency tones like a hearing test because it has high resolution and it dissipates quickly. If you want to give away your position to everybody in the northern hemisphere, you put out low frequency pulses like you always see in Hollywood, which they don't do. High frequency attenuates quickly in the world that we live in. So going through the cabling, the high frequency, this rise and fall time, so if you made a sine wave out of this, you'd be well over 5 gig. But here they're eye patterns, they're 1s and 0s. So you lose the rise and the fall. Quickly, you lose the amplitude. So what you end up with in long run of cable is a low amplitude, instead of a square wave, a sine wave. It rolls off, you lose the high frequency. And that is what your receiver is trying to lock to. If you look at this like a bicycle chain, like film sprocket holes, teeth on a timing belt on an overhead cam engine, it keeps the transmitter and the receiver locked together. On a bicycle chain, you start filing off the teeth, eventually the chain starts to slip. It's the same way here. If you have jitter, you have frequency instability. This is moving back and forth like a bicycle chain that's too loose. Eventually it falls off the sprockets and that's the end of it. This is time. Passive devices like cable, you lose the high frequency, you lose the amplitude. Active devices that have circuitry, you have timing issues. How much jitter do you have? The higher the frequency of the jitter, the less of less of a problem it is. Lower frequency jitter, like we'll go through some slides here that show you, this is a 10 hertz filter, 10 hertz high pass. You run through various filters and you say, where is the jitter the worst? Test equipment, I get asked this all the time. Karl, look at this problem here. How do I fix it? We've identified the problem. Now you need to call whoever made that black box and say, here's what I found. Now you're having intelligent conversation. It's not name calling, it's not finger pointing. Probably never happens where you work, but there's a lot of finger pointing in digital video. Sure, where you work, everybody says, step aside, it's my problem, let me fix it. It doesn't happen. So by having test equipment, looking at the physical layer, whatever, it allows you to have intelligent conversation with the person that hopefully on the other side of the phone can help you. So we have jitter issues, frequency and stability. How stable is the circuit? Stability costs money. Especially start going high def, 3 gig, high frequency stability costs a lot of money. So when you're evaluating equipment, some people I know never look at an iPad, or oh, we'll buy this reclocking DA and this and that, and never look at the physical layer. That's actually the quality of the signal that you're pumping throughout your facility. How healthy is it? It doesn't get more stable with time, it becomes less stable. Heat issues. From jamming more and more equipment into smaller rack space, heat goes up. Heat is noise, noise is instability of a clock, and you start getting jitter. Eventually, interoperability, the digital cliff effect, you have a wobbly circuit, eventually the signal on the other side becomes unusable. Demodulated jitter. We have the I pattern. Now this is beating 2 frequencies together, and this is a difference. In test equipment, hopefully, there's a very stable clock. You take the signal coming in from the outside world, you beat the 2 together, you get a difference. Unlike in the cardiac intensive care ward, here a straight line is good news. That is the fingerprint of the frequency instability. So when you're complaining to a manufacturer, here is the pattern I'm seeing at this high-pass filter. You run through 10 hertz, 100 hertz, 1 kilohertz, 100 kilohertz, and you see how that changes. That's a signature of your instability. Is it a switching power supply? Is it word correlated? Is it frame correlated? Is it line correlated? All these things tell the person you're talking to in technical support what your problem is. They will say, okay, what firmware are you running? Is the cooling fan working? Do you have ground loop problems in your building? What is going on? Now you're having intelligent conversation. Stressing your signals, stressing your facility. This is a pathological test signal, not very exciting. It's magenta and it should be more of a gray than it is at the bottom. This is what you want to put into your system to break it. In serial digital video, there is a pseudo random scrambling algorithm. So when you put the lens cap on, you don't get all zeros. You zoom into the sun or bright light, you don't get all ones. In serial communications, it's self-clocking. You don't have a separate clock like you do in parallel circuits. Serial, the receiver is clocking off the signal actually coming in. So what you want is maximum transitions between highs and lows in serial communications, which is exactly opposite of parallel. You want the least amount for crosstalk issues. So what we're doing, Tektronix developed this signal 10, 15 years ago now, that breaks the pseudo-random scrambling algorithm. This one up here forces cable equalizer testing, 1 high, 19 lows, 1 high, 19 lows, like filing off teeth on the bicycle sprockets. This down here is 20 highs, 20 lows, 20 highs, 20 lows. The receiver does not want pulsed DC. It wants maximum transitions. This test signal here is the opposite of that scrambling, so we end up with this. So if live video looks good, color bars looks good coming out on the other end of whatever you're testing, you put this signal in and you see this, you've not fallen off the cliff. If you put this in and you see nothing, you're living on the edge of the cliff. So this forces you that much closer to making the plunge before you actually get there in normal operation. So if you see this, video looks good, color bars looks good, you put this in, you see this boring test signal here, you add between point A and point B more cable, 50 feet, 150 feet, 300 feet of cable, whatever it takes to make this go away, and you document that. That's now your baseline between here and there, the health of the connection. Because signal quality does not improve with age. From the moment you take a piece of coax off of the reel, it remembers everything you do to it. A wise person once told me, cable does not get mad, it gets even. It remembers everything you do to it. You drop the raised floor on it, you jam it in the rack and you fold it over, you over tighten the wire ties. Nobody's looking, you stretch it, it's a little bit too short. It's permanently impacted. These frequencies, 1.5 gig to get over a third order harmonic through it, you're talking high frequency RF. So it's flexible waveguide we're dealing with. Ntsc, the good old days, was 4.2 megahertz, analog megahertz. Here we are, 3 gig to get a square wave to go through it. Flexible waveguide. So what is the health of my ones and zeros coming out the other end? Does not improve with age. Every injury you do with your reflections, your standing waves, impacts the health of the ones and the zeros going forward. Reflections and all that stuff add up. Gamut and monitoring. This is actually what you're deriving from those ones and zeros. This is not what you actually are putting through the cabling. There's still people in the industry that think this is like analog. You put up an oscilloscope and you get a waveform. No, you get ones and zeros. I get dragged into this conversation on a regular basis, post houses and whatnot. Karl, my people will not look at a waveform monitor. They're artists. They don't look at that green thing over there. That's an engineering thing. We're creative, we're not engineers. And he says it's killing us with quality control issues. I usually say it sounds like a management issue to me. You have people working here that aren't following the rules of what it takes to get the job done right, and you have customers that are rejecting your work. Karl, come in. You're the expert from out of town. Remember, an expert from out of town means you had at least a 2-hour drive to get there. You can't be an expert if you're from across the street. You're just not an expert. You know, there's a guy across the street. Karl's from DC. Oh, he's an expert. So I get dragged into this one for quite often for similar reasons. So what I started out with, exactly what they don't want to hear. Gamut can actually, not maintaining color space, can actually wreck your system. The cliff effect. Pushes you off the cliff. Now, like analog, you can have a lot of things wrong and things still come out the other side. Here, you can actually push yourself off the cliff. So what we're doing, trying to maintain 0 to 700 millivolts. Maximum white, this is my Y channel. Minimum black, there's no super black, it's 0 to 700. For chroma, my color difference, 0 plus 350, 0 minus 350, 0 plus 350, 0 minus 350. Can't go below here, you can't go above there. You can try, and it might look really cool. You have a real high pressure producer, which exists. I want you to crank up that yellow. I want that cheeseburger to pop off the screen. Client comes in, I've never seen our cheeseburger look that good before. What a great place. That's a good-looking cheeseburger. And it goes to air. And they're horrified. Why is my cheese and that cheeseburger green? What happens? Or why does the picture twitch when the cheeseburger comes in? That's not what we're paying for. This is an outrage. How can they do this to my cheeseburger? Because you can break the rules of interoperability. You know. Continue along here. I try this. This is called split diamond. It's the same thing, 0 to 700. Here's my 0, and my 700's here, and off to the side, color. So it's luminance, straight up and down, color off to the side. So I've worked with colorists, and they say the first thing they look at, how true is the grayscale? If it's not gray, is it a mistake, or is it an artistic approach to the video? So what we do here, black is here, gray to white. Black is here, gray to white. green, green, blue, red. So it's a way to visualize luma and chroma one test. If it's inside the diamond, you're not breaking any rules. If it's outside the diamond, you've broken some rules. Okay, fine. Is that any easier than a waveform? Maybe, maybe not. It's another way of visualizing exactly the same thing. So live video, if it's inside here, you're okay. If it's outside, you're pushing your luck with interoperability. Ntsc color space, kind of hard to see here, but Ntsc. Why do I care about Ntsc color space? I'm living in the world of HD. Are you ever going to down convert that to Ntsc? Some people say, we'll never do that. Well, great. If you have content that is of high value, it's going to go to Canada, Mexico, it's going to be archived, it's going to be seen on a negative, on an analog tier of a cable system. Ntsc still exists. So Ntsc color space, this is really tough to see, I apologize. My vertical axis is black here, white there, color off to the side. What you're trying not to do, really hard to see, 120 IRE, remember good old IRE? You don't want to go above your 130 line, definitely, because you overmodulate the Ntsc transmitter, the Ntsc modulator. What happens if you do? You get buzz in the audio. Still exists. So if you crank up your chroma too much, you'll get that. And yellow would be up in here. And yellow people like to crank because yellow looks nice on TV, it makes people happy, it makes you eat faster, spend more money. Yellow is everywhere. You go into retail, there's a lot of yellow. So yellow, everybody gets carried away with it, and we have issues there. If there's no automatic color correction, you get buzz in the audio, very unpleasant. You go outside your 6 megahertz channel, you're a noisy neighbor. Every time you play the cheeseburger ad, your neighbors see noise in their picture. If the neighbor is the FAA, you'll hear about it. So Ntsc color space, if you're concerned with it, here's a good way to visualize it. If it's under the red line, you're okay. Looking at our arrowhead again, you want to crank this down a little bit. Here you're okay. And I saved this for last. If you don't look at any of that stuff, turn on Picture Bright Up in your configuration menu. If anything is oversaturated, as far as the color, too black, too white, you get this checkerboard in here. You have to be totally untechnical, let's say, to not understand. Well, I want to get that out of my picture. If this black was too black, I want to bring up my blacks a little bit. My sun is up here, I want to bring down my sun a little bit. I oversaturate with the yellow, the red, the whatever, you get rid of the checkerboard pattern. There's no checkerboard, you're illegal. There's no interoperability problems. As I mentioned before, running your facility as an intensive care ward, we have session screens because you need to be looking at the audio, the video, the physical layer, so video session. What format is it? Do you have start of active video problems, field length, line number? If green is good, red is bad. Do you have any stuck bits in your 10-bit signal for luma and chroma? Do you have any gamut issues? Do you have any CRC, checksum errors? It's a good way to see what's happening under the hood, behind the scenes in your signal. Ancillary data space. In digital communications, if you don't need it, you don't send. Why digitize something that nobody needs? Doesn't make any sense. But a different way of looking at it also, if you know you need it, you know exactly where you need it and how much you need, you still won't send it because it's predictable. It's not information, it's redundant signal. So what we do in digital, first thing we get rid of is your vertical blanking and your horizontal blanking. It's gone. That's now free time and space in the world of electronics that we have on every frame, every line of video. What do we put here? We put ancillary data. How do we synchronize a signal? We go from analog to digital, we get rid of the sync. It's on every single line, every frame has it, we get rid of it. If I need it, when it goes from digital back to analog, I put it in information. Why transmit something I know exactly where I need it and how much I need? How do we synchronize this signal to digital domain? It's called end of active video, start of active video. I'm scanning along this picture. Back in the old days, we had our sync and chroma burst and all that good stuff in here. I just put in 3 10-bit words that replaces all that. It's called end of active video. We have a 10-bit signal. We put in all ones, 3FF, 10 bits, followed by all zeros, all zeros. That's the secret code that tells the receiver, wake up, something is going to change. It's no longer luma and chroma. Going across here, it's still flowing the same bit rate, but now it means something else. In digital communications, unless the receiver knows when something begins, it can never lock anything. It's meaningless ones and zeros. It has no meaning to the receiver at all. So I put in, as I'm scanning across here, all ones, all zeros, all zeros. It tells the receiver, wake up, I'm going to send you something else. Not luma, not chroma, it's ancillary data. It's 16 channels of embedded audio. It's closed captioning. It's ancillary data. And then I get finished with that through my 16 channels of embedded audio. I tell the receiver, wake up, start of active video. I put in all ones, 10-bit, 3FF, all zeros. That tells the receiver, wake up, something's going to change now. You're back to luma and chroma with the same ones and zeros at the same bit rate. So I have Hank and Brother Vank, free time and space to put in something on every line or every field of video. And I put in ancillary data. How do I tell the receiver, you're starting something? I say, I'm ending it, now here's what I'm starting. I put in exactly the opposite, all zeros followed by all ones. That tells the receiver it's ancillary data. So if you see where I'm going with this, as far as controlling your gamut, your color space, you don't want to be tickling up against all ones and all zeros for artistic reasons because you're breaking the system. I can be scanning across a line of video up here. If the whites are all ones and the blacks are all zeros, as I'm scanning across every pixel, I'm telling the receiver something is changing and it's not changing. It's luma and chroma. So that's why your artists can cause trouble with your signal even surviving because of this fact right here. And then I have to tell the ancillary data what type it is. I have a digital identifier, a secondary digital identifier. I have a data count. I have your attention. Here's what I'm about to send you. Here's how much I'm going to send you. Now here's the payload. Go make some audio. And this happens line after line after line. So we have a data channel within our video picture itself. How do we analyze all this stuff? Came out with this about almost 2 years ago now. Ancillary Data Inspector. This tells me what's in the feed. I have a list of Smpte 299, my closed captioning down here, embedded audio, and this tells me what's in. I can look at it 3 different ways. I can say out of all the standards in the world, what's in my feed right now. If it's there and present, you get present and okay. If it's missing, it says missing. If it's present but not okay, it says error. If I'm worried about ancillary data coming from China, you enable that. If you care less about Chinese ancillary data, you don't test for it. So then you would go to a watch list saying, I care about these and tell me if they're there. Or another mode is tell me what's there right now. Green is good, okay is fabulous. It tells you what field, what line it is, what standard it is. Then you highlight it, you scroll up and down, gives you a data dump. Checksum. Expected and actual, do they equal? If they equal, then the ones and zeros sent are actually received. What this all means, I don't know. You call up the spec for 334M, and it will tell you what it means. If these values equal what the spec says, you're in good shape. If they're different, that's where you have your conversation with the manufacturer that's causing the problem. Why is this coming in good and not leaving good out of your unit?
I have a ignorant question.
No, please go ahead.
This is all assuming that the sink has been established somewhere else. There's no recovery of sink embedded in any of the mature testing.
The
The
N,
only thing that came to it was the,
EAV and SAV.
So they are.
That is your sync.
So if they don't show up in the frame somewhere in the system,
It would know what to do. Could make sense out of anything. EAV and SAV are all ones, all zeros, all zeros. That is your synchronizing for every line. You got it. Closed captioning, you can have 608, 708. I know Jerry's an expert in this field, so if I need help, you can bail me out. 608, 708, you can see both simultaneously because you might have for SD or HD before the encoder, before the uplink, downlink, wherever you're looking at it, it's nice to do a comparison if you need to. It actually displays it as it should be appearing on a consumer's screen. You highlight what you're looking at, gives you data dump. We also have ancillary data status, kind of a higher end user view. If everything's green, you're in good shape. If something's highlighted in red, you want to drill down and see why it's red, why do you have an error. So ancillary data, where is it, where isn't the problem? You can have a global feed, you're putting it in, somebody's not receiving it on the other end. Where does it happen? Somebody somewhere between point A and point B is corrupting it or removing it or putting something on top of it. AFD, anybody doing AFD? Usually one in the room. AFD essentially would put my retired dad out of business as far as one of his hobbies. That's playing with his home theater, playing with the screen sizing. Does he want to see the crawl or not see the crawl? Does he zoom or not zoom? Until eventually he gets a postage stamp in the middle of a 65-inch screen. My mom says, why does he keep doing that? It's like, I better stay out of this one. AFD would put him out of business. AFD is put in by the creator of the content to tell the 4:3 of the 16:9 screen how it should look. Is it pan and scan? Is it center cut? Is it pillar box, letter box? And that's the way it is. It's got to be put in. You got to have a receiver that can actually do something with it. Anybody have any idea of how many consumer devices, what percent actually has AFD enablement?
Is it supposed to be in all the ATSC chips, or is that not part of it?
I don't know the answer to that. Jerry, can you help me with that one?
Notice that is that there are millions of ATSC devices between
Yeah.
It's the same space that we spec.
And the use of the word is primarily using this for distribution as well as receiving or station receiving or station receiving. And what happens after that is Mr.
So AFD, for example, if we would show you the highlight of what it should be for 4:3. Loudness. Let's jump right into that. Keep moving here. Well, it's the subjective measurement. Different people perceive loudness differently. And there lies the challenge. How do we have an objective, repeatable measurement of something that is very subjective? Well, we have to come up with a technique for doing that. So we need filters that mimic how the human ear responds to sound. What frequency, what amplitude. Dialogue normalization. This is metadata put in at the encoder. Dolby encoder that tells a Dolby decoder in the person's home, for example. It presets the volume. On a block diagram, it's the block before the consumer's volume control. So it presets the volume. So that's an important aspect of loudness. Is that being done properly? No, it needs to be monitored. Dynamic range control. What is dynamic range? How loud is loud? How soft is soft? You go to a movie theater, you want to be blown out of your seat with the explosions, and it's nice and quiet, you can hear the crickets chirp. You don't want that experience in your home. Most people don't want it in their home. They want the explosions here and the crickets up here. You can hear the crickets and the explosions are acceptable. So what's the dynamic range? Where is the dynamic range? Up here, down there. Loudness is here, dynamic range is here. Dialogue normalization is presetting the volume control for the consumer. And they can do what they want. So we have standards. 1770, 1771 are used by the ATSC to come up with their nice recommendation we're going to go through here. 1770 is the algorithm for measuring loudness and true peak audio levels. How do we represent electronically how human beings perceive loudness? 1771 is how do we show this with a meter? How do we represent this so people understand what it means? The ATSC came up with a very nice document, A85, which I'll share some parts of it, is actually nicely written. The P-Loud Working Group, Europe and different parts of the world, this is their interpretation of loudness because they're having the same issues because with digital audio we have a lot more dynamic range. People are tired of being blown out of their seats at home. Measuring loudness. I have a filter, two filters put together. This one is flat over 1K. This one is flat, then it goes up around 10K. Find this one interesting, the acoustic effects of the head. Our sound does have resonant frequencies. Without getting too graphic here, like most medical things, if you know nothing about it, you're probably better off. But my brother-in-law had a brain tumor, so they took out this part of his skull, which is the thickest part of your skull. It's filled with resonant cavities. Your entire ear mechanism is embedded in bone, which resonates. So not all of our hearing is through our eardrum. It's through this part of your skull and the resonance of your head. So that helps you with localizing, is it in front of me? Is it behind me? Is it high frequency? Is it low frequency? So once you lose this, you lose a lot of that ability, I've learned. So interesting part of the algorithm.
What that's doing is actually not accounting for resonance, but shattering effects. Because it's a boost of high frequency.
Good point. Right. How do we come up with one number? What we really want for operations is one number. Am I too high? Am I too low? Where am I? So we have the ability with the filtering to come up with a summation, to say, give me a number. That magic number is -24 LKFS. True peak, 4 times over sampling to catch the highs. How high is high? You can't go above 0 in digital audio. Usually -3 is a typical number that I've seen, but you don't want to clip. Unlike analog, you can't just keep cranking until things blow apart and go up in smoke. In digital, it just doesn't work anymore if you keep distorting it. Nice part about A85, I read specifications, I'm sure you do. Sometimes I say, I understand this, I can go out and do something with it. Sometimes I read it two times, 3 times, it's like, what the heck am I supposed to do about this? It's interesting, it's technical, but so what? What do I need to know? What they came up with, Ntsc, quick reference guide for people running stations, cable networks, satellite networks. What are they supposed to know? What are you supposed to actually go out and try to achieve? Run through this. Anchor element. What are people actually focusing on when they're listening to audio? Usually it's dialogue, music, whatever. What is anchor element? Dialogue level, LKFS of the anchor element. Terms are getting us up to speed on. Dialogue normalization, we talked about that. LKFS, LKFS. L for loudness, K, the alphabet. We had the A-weighted filter back in the early days of Bell Telephone and whatnot. Now we're up to K. This is the filters we talked about a few slides ago. FS for full scale. Loudness, K filter, full scale. Target loudness, what we're trying to achieve with the anchor element. Long form content. You're not focusing on shouting or whispering. It's what you're typically adjusting your volume to. What the viewer would focus on to set the volume. Point we're working up to here is you need test equipment to measure it, to document it, but you still need people to have a clue what they're doing with audio. Hopefully that fits into the business model. Short form content, a little bit more of a challenge. How short is short? Sometimes real short. Is there anything to focus on? Becomes the challenge. Newscast, live programming, it's all the same. The end user does not care if it's coming in on a satellite, playing off of a server, or it's right out of the studio, or it's being shot in their front yard. It doesn't make any difference. They want consistent audio levels. file-based content, it makes no difference. You need to monitor it all and record it. Interstitials, same idea. It's all content. Local station should receive it at a fixed loudness. You still need to monitor it. You're trying to be a pass-through, but how good is what's coming in? Because you're responsible for what goes out. Pretty much covered that. Keep moving here. Dynamic range control. You have line and RF. You're not trying to get the theatrical experience at home typically, so you crunch down the dynamic range for line, and even more with RF, good old channel 3 and 4 type modulation. Annex for quick reference guide for people actually creating content. Monitoring environment. This is an important aspect here. Monitoring environment. You need a human being that can actually listen to sound. You try to have, in the world of science, you have your constants and you have your variables. The variable should be the content playing. Is it louder or softer than what it should be just by listening to it? So that means your listening environment should be as fixed, nailed down, static, whatever, as possible. Not every time somebody walks in, they fiddle with the volume control and re-equalize everything, trying to have some consistency. So if you say leave the volume set at 11, you leave it at 11. That way, if the volume goes up and down with the content, you're experiencing it as it happens. Target loudness. According to the ATSC, we're trying to achieve -24 loudness, K-weighted filter, full scale, plus and minus 2. Green is good, yellow is you're out, red is a big problem. So we're trying to maintain -24 LKFS. As far as our reading, talked about that. Keep moving here. How do you monitor multi-channel audio? Do you have 5.1? Do you have 8? Do you have 16? Do you have 32 channels? What do? You need to monitor it. You can have DVFS, you can have loudness. For your surround sound multi-channel, you're sitting in the middle here. You have left, center, right surround, left surround. So you can visualize your audio is what you're trying to do. And showing here, once again, the surround sound representation of it. Left, center, right surround, left surround. And off to the side, your tick marks are where the brain would say the sound is coming from. Is it a pinpoint of sound or is it a broad sound? And by changing the phase between the two channels, left, right, front, back, whatever, the more in phase they are, the brain perceives it as more of a pinpoint of sound. The more out of phase, the more from a general area. So you can visualize the artistic effect of what you're trying to achieve with your surround sound. There's our magic meter once again, -24 LKFS, what the ATSC is recommending. And the same thing again. With digital audio, something I learned the hard way. In analog audio, when you have nothing, the more nothing you have, the happier everyone is. You want -90 dB. Telco silence. I don't have hum, I don't have hiss, I don't have crosstalk. I have electrically nothing. You're delighted with that. In digital audio, when you have nothing, that's a serious problem. Because you need something to have silence, to have mute, to have low levels. Still needs to be ones and zeros flowing at the same bit rate. It needs to be constant flow of a signal. So with that said, when we have a problem, loud, quiet, gated, unlocked, CRC errors, it's nice to have an indicator on your meter for why you have what you have. If you have no signal and it says CRC, you have a garbage signal coming in. If it says unlocked, you probably have nothing coming in. So it's nice to know what you have and what you don't have. Audio sessions, once again, our intensive care ward stuff. This looks at all the aspects of the audio, channel by channel for clips, overs, loud, mutes, silence, your averages, your loudness readings, and it documents that. For your troubleshooting, loudness sessions, since at some point fines might be awarded to people, how do you cover your butt? You need to document this stuff. So what we do is we document it second by second. So that way, if there's any dispute, you can go back and somebody says, well, at 4 o'clock yesterday, you blew somebody out of their seat. Go back to your log and say, you're right, we did. Or, nope, sorry, we didn't. So it's somewhere else. Where's the problem? Where isn't the problem? Here's something to think about. Tell me if I'm on the right track or this doesn't make any sense. You're running your facility to the letter of the law. All your content, negative 24 LKFS, it never varies. You run a tight ship. But you're getting complaints for being too loud. Let's say another network is running low. People watching their favorite show, they crank up the audio. What do people do on the half hour? Channel surf. They come to your network, your channel on the half hour. What's the first thing they see? The sham wow guy or something like that, right? Wow, this is an outrage. I'm tired of this. You know, I'm calling the president, whatever they're going to do. You get complaints because somebody else is running too low. You might get to that point. Think about that. But anyway, documenting it second by second. There's a macro you can run that downloads the log every 24 hours, and that way you have an archive of second by second time. You can chart this by 90 seconds, 180 seconds, up to 6 hours. So you can see if you're in, you're out, green is good, red is bad. Just expand this out to whatever time you want to see. Export it, you put it in an Excel spreadsheet, you can make all kinds of cool graphs and charts out of it, whatever you want to do. AV delay testing. 0 time. Video is always the reference. Audio is either late or it's early. Video is time 0. In our normal everyday experience, you see there's a difference here. Delay, we have a lot of threshold for acceptance. Advanced, not that much, because you walk outside, you see a bolt of lightning. If it's your lucky day, there's a long delay before you hear the thunder. If there isn't, don't worry about it. And you're watching TV. Batter swings the bat. See the ball fly, then you hear the crack of the bat. We expect that in our everyday life. We don't expect to hear things before we see things. That's very annoying. If somebody's on the fence, you know, their finger's right on the remote control, and lip sync can be out. They really don't understand what it is, but they're not quite that happy watching this program, so channel surf right on through it. It can affect your ratings. File-based QC. We can get a whole day of this tomorrow at Stonehill. I'm not presenting tomorrow, I'm attending. File-based QC. Back in the good old days, we put in PAL, Ntsc. Back when I first got involved, my first digital project, that's all we had with Ntsc. We do an A to D conversion, we encode it, store it somewhere, we broadcast it, whatever. Life was simple. By QC points, you have a file somewhere, you play the file, you have 1 hour of content, hit the play button, you kick back and you watch the content, your admin time, a little bit more than an hour, half hour, whatever. It's pretty much close to 1-to-1. But this is the world we live in now, and it's getting worse by the minute. It's like, why all these different formats? Why all these wrappers? To make our life more complicated. What are your QC points? Do you have time to QC? I don't know what you guys are doing, but I go to facilities, they have 1 hour of content, they flip it to 7 or 8 different formats. If you're doing 100% QC, multiply 1 by 7 or 8, that's your QC time. It's getting worse. People going to adaptive streaming. You can have one file type at different bit rates. Multiply it again there. Get to the point, people say, well, we'll 100% QC this the old-fashioned way. We'll spot check this. Over here, well, we don't have time until they get burned. And it's back to 100% QC, which is unmanageable. It's inconsistent. It's actually a waste of time. You need to automate the process. You're not replacing people. Say, well, I need my people. Yeah, you do, but you need to put them where they're needed. If you're testing a file and it has fatal interoperability issues, it's the wrong compression for this deliverable. It's MPEG-2, it's supposed to be H.264. Hit the play button, no, it looks good. But it's the wrong type of file. You need to automate QC to say, that's instantly rejected, it's wrong, here's the error log, waste no time other than saying, why is this wrong? Or, if it's 100% meets all your test criteria, it gets a green light, it's ready to play. You want your talent, your golden eyes and golden ears, the stuff in the middle. It's a little too blocky. We have some gamut issues. There's 25 seconds of black in the middle of the content. There's a minute of silence. Well, is that artistic or is it a real problem that we have? Is the gamut issue somebody got carried away with the cheeseburger, or it's the green screen of death that is oversaturated green? What is it? That's where you want your golden eyes and golden ears to pay attention. The stuff that's in the middle, that somebody really needs to make a decision. Do we accept it? Do we fix it? Do we reject it? Do we re-encode it? Do we tell the producer to never do that again? What do you do? That's where you want to put your talent. Start the beginning at ingest, because that's garbage in, garbage out. You need to understand what's coming from your providers, what you're creating yourself. Is it any good? File-based content, process steps you have where you go through encode and recode, repurposing different bit rates. It gets complicated pretty quick. If you truncate a file, you have incorrect separation of audio and video, you have significant opportunities for things to get messed up. Human inspection, as we mentioned before, there he is. That never happens where you work, I'm sure. Everybody has their eyes glued wide open. Human inspection it's subjective. I mean, one QC person doesn't necessarily see what another person sees. Can they see every slice error? Do they see every gamut error? Start getting into frame rate, bit rate, pillar box, letter box, play time, your color space, black at the beginning, at the end, in the middle. Blockiness, that's a big one, because not all content has the same requirements as far as being blocky or block-free. It's not all the same. So you can set different criteria for blockiness. Audio tests, the same aspects. We look for clipping, mutes, test tones, where they should and where they shouldn't be. System level tests, not going to get too deep into this, need to keep moving here, but you go through and configure it for what you consider your pass-fail. Things like interoperability for syntax, it's either you test for it or you don't. If it fails, it fails. But things like blockiness, color space, how much silence is a problem, that's where you need to go in and configure it to what you're expecting. Green is good, red is bad. Blockiness, you can see you can go in and do how much of your screen for luminance, 5% of the screen, 10% of the screen, you decide. Blocky, but technically it's okay, that's pretty noticeable. Look at loss of video, is it black or is it nothing? Pillar box, letter box, silence. 3D, anybody doing 3D? How easy is it?
Depends on the project and depends upon the people you have to satisfy creatively. Big question. Technically, it's easy.
Well, I
Setting people's
totally agree.
expectations is hard.
Yep. I worked with a few people that are doing it, trying it, succeeding at it, some of them. There was this being overly optimistic that we can have a 3D rig and we'll only use the left eye for 2D and we'll use left and right for 3D. We'll just do this all over the place until people realize you can't do that. I'm working with people that are doing live 3D hockey, and they have 20 cameras for 2D, old HD, and they have 4 cameras for 3D. By adding those 4 cameras, it's 6 times the cost of doing just 2D, because you need extra days of setup, you need twice the amount of people to sit there and fiddle with everything, and every time you make a change, you have to readjust everything. You take matched lenses. You get the best lens guy you know and say, I want matched lenses. You zoom in, you zoom out, they don't track. You actually have to have a lookup table processing to make sure they line up. It's to that level of complexity. When you're shooting a hockey game, the scene between the glass, you're watching on 2D, it's a scene you kind of ignore it. In 3D, it's poking right in your face. It's unacceptable. By using a mirror rig, by shooting through the mirror and shooting through the glass at the hockey game, there's a polarization effect that makes the advertisements on the opposite side of the ice look like they're floating out over the ice. Very annoying. You actually need 2 separate production crews, start to finish. Different announcers, because the shots are totally different. With 3D, you're trying to get the skaters to come into the shot and leave. It's like, oh, that's a wonderful shot. There's not a lot of zooming and panning and following. It just doesn't happen. You can't do it. I mean, for Hollywood productions, that's what people expect. For sports, business case is going to be hard to prove.
We
Where-
get the radio. They're describing.
Yeah. That makes sense. Turn off the TV, all the other audio. Anyway, I'm just going through this and hearing what people have to say about it. It's a real challenge.
One of the key challenges that sports demands a lot of telephoto work. Telephoto work creates pop-up Christmas cards in 3D.
Yeah.
Because the standard of viewing is a 30-degree to 36-degree view angle. When you do a telephoto zoom in, suddenly you've zoomed in on what is about a 6-degree view angle or tighter. So you have basically you have a pyramid violation in the optics.
Good
That's
point.
what
Good
creates that
point.
effect.
Good point.
The presumption and the illusion is that the viewing angle of the taking system is the same as the viewing angle of the eyeballs. When you violate that, you break the 3D effect. And sports screams to violate that when you're covering big field work like baseball.
Yeah. Sports is what's going to pay for this if it ever happens.
Well, therein lies the challenge.
Yeah.
3D demands to be a close-up medium, and that's not always possible with sports.
The bean counters and sports networks, they're always trying to do more with less. Now
Yeah.
you're introducing a technology and production method that costs way more. You keep charging more.
No, that's it.
Business case. Is that? You're not gonna, your advertising not gonna take it off. They're gonna want their ads on the 3D and the 2D at the same price.
Yeah.
The irony is that in learning basic photography, the first thing you're taught is that all the interesting shots happen at the extreme range of your lens.
Right. Yeah, that's true.
Very narrow, very wide, that's
Mhm.
where you find it. And if you're just shooting normal, the shot is boring. All the 3D stuff begs to be shot with a normal.
That's true. Good points. Thanks.
And the 3D stays on a shot for a long period of time. You try cutting quickly in 3D,
No.
you have people puking. Seriously.
Yeah, that's true.
Were you folks at the meeting 2 months ago with John Gill predicted that 3D would be
Yeah, and everything will be 8K before we
That's fine. I mean,
Well, going to be interesting time.
Right.
Well, his point was, he had just seen gorgeous, and you go in there and it's like, total high, 50% conversion from the quality of the image. That's what we're doing.
Well, I like the 8K for 8mm, that's a K per millimeter, that looks great.
I'm sure you know there's beam splitters with mirrors. That way you can adjust everything, and you end up with flipped and mirror images. So you have to be able to process for that and line everything up. One of the obviously there's a lot of development going on at Tektronix right now with a moving target of 3D. One thing I've learned in life, when I look at something the first time, it's like, it doesn't make any sense. I don't care about that. Then all of a sudden, I realize that's one of the most important aspects of what I'm trying to learn here. And this screen is one of those. The checkerboard. I first looked at this, I said, that's nonsense. It's like a gimmick. Well, no, it's not. 'Cause what it's doing is taking the left and the right eye. It could be side by side or discrete dual link, and it takes left eye, right eye, and puts them on the screen. I've taken this to a few networks, and they said, this is a screen we're going to leave up all the time. If you don't notice a checkerboard, that's a good thing. If the checkerboard jumps out at you, you have a problem between the left and the right eye. If you have darker, brighter, they're not even between left and right. You have difference in chroma, the checkerboard jumps out at you. Focus, it jumps out at you. Time, you can have timing difference between the left and the right eye. Shift horizontally and vertically, the checkerboard makes it jump out at you. So places I've taken this, they said that's we're going to let up. That's what's going to be up all the time. You can just walk by here and see no checkerboard, life is good. See a checkerboard, hey, we got to do something about it. One of those things that when I first saw it, I said, eh.
I noticed on your screen it's 16 by 9 on the checkerboard itself.
Yes.
I'd be interested in a 24 across.
Haven't heard that one yet, but that would make sense.
And to keep the same ratio. The reason I say that a 24 across is really close to 4% of screen width.
Okay.
That's a useful number for 3D.
Not aware of that. We didn't
It's
put-
double the 2% maximum IoT spacing. So you can look at the screen and actually know, looking at the grid,
Mhm.
how far things are going to be separated in free space. You can do the math in your head very quickly when you have a known reference.
Interesting point. You can look at a waveform, your highs and your lows, see how things are mapping between the two. You have left and right for two cameras. You can do matching. Difference mapping. If I have, I think there's a better screen coming up. Here it is. If I have left and right eye, if I'm doing a mirror rig adjustment, I'm zooming in, zooming out, I'm focusing left and right. If this is a blank looking neutral medium gray screen, they're exactly the same left to right. Right now this would be in left minus right, let's say, which means medium gray, the sky, there's no 3D to it. If it's whiter than medium gray, it's the left eye. If it's darker than medium gray, it's right eye. So difference map without glasses or anything, you can see the 3D effect between the left and the right eye.
It depends on which way the transition's going.
Or you can also do right minus left. You can do it that way too. And there you can see the lifeguard stand. And what we have here is actually a color. Should be. It's actually what you're looking at, left and right eye put together. And what you're seeing, if you put on your 3D glasses, your red and cyan, or your green and magenta, it looks like a black and white 3D picture. So you take your glasses off, the color is left eye, right eye. So it's another way of seeing 3D. And the slide that I didn't put in. This would also be a way of testing your disparity. A new thing we just added that I didn't get the slide in, I thought I did, but it's not here. You have a grid, vertically, horizontally, that gives you screen percentage. Because typically from what I'm hearing, you try to be less than 1% towards you, 3 or 4% away from you as far as disparity. So
That was what I was talking about by aligning your checkerboard to it.
okay,
Your checkerboard could do the same thing as the grid.
good point. Yeah, that would work the same way. You're right. So you have a grid. That way you can see if you're violating in front of you or deeper into the screen. How do we transmit this stuff? We can barely fit 1080i into a 6 megahertz channel, so we do side by side where you do a full left eye, you squeeze it to the left, right eye, squeeze it to the right. That way it fits into a cable channel, satellite channel. Or you do top and bottom. So essentially, that's what I planned on covering tonight. 8:30. Any questions, comments? Stick around, ask questions. Yes?
At the beginning of your presentation, you talked about getting baseline for your SDI signals or your digital signals, and then comparing them to a problematic signal. Is there
anything within your, obviously your test equipment capabilities that can essentially just point out those differences when you're comparing one signal to another numerically? In other words, forgetting about the stuff that's okay, but
Yeah.
just those points that are bad, short of green or red.
Well, I didn't get into it. You really get deep as far as the error logging, the analysis screens. There's a whole bunch of status screens I didn't really get into tonight, but you can drill down. If you take let's say if you suspect it's this device here, the signal's coming in good, you don't have any error log issues, you don't have anything wrong on your status screens, but coming out of it has error issues, you can do an A/B comparison between the in and the out, you can do that.
Right.
Or you can put in a test signal. We have test signal generators that put in a known good signal.
On the subject of your test signal generator, the signal that's supposed to screw everything up, what's that called? The
Pathological.
pathological
Yes.
signal.
Mhm.
Is that an optional signal, or does it
No.
come standard with your test generator?
Every signal generator we've had for
It does, okay.
10 years or more does it, yes. Yes. Good, we're breaking the system.
We actually had a problem with that once where a deserializer, back in the original SDI days,
Mhm.
we had a deserializer that certain things would break it. And we couldn't stop working. So we really didn't have time to fix it, and we really didn't find it. So we just ever so slightly increased the horizontal blanking so that every line had a little bit of black at one edge. That gave it enough to get the clock going, and it worked fine.
Interesting approach. Anything else? Appreciate taking the time out of your schedule and sharing the evening here, and thank you for.
Thank you, Karl.